Okay, so what I was trying to say in the last video is that this is more complicated to do because you have to kind of back everything up one for the circumscribed. This says inscribed, it should say circumscribed rectangles. So what you get is 2/5. So when you do one with the I minus 1, you get basically f of 0, and then when I is 2, you get f of 2/5, and then when I is 3, you get f of 4/5, and so forth. So that's why you can, use I minus 1. But when you sum this time, you actually have to sum 4i squared, because when you square this, you get 4i squared minus 8i plus 4, and then over 25, and then you can factor the 2/5 out. Let's see, I did that, and then the sum of 5, of course, is just 5 times 5 like it was before, but here I factored a 4/25 out, so that way I just got the sum of I squared minus 2i plus 1. Well, the sum of I squared, but like before, it's 5 times 6 times 11 over 6. The sum of 2i is 5, the sum of I is 5 times 6 over 2, because remember n is 5. And then the sum of 1, as I goes from 1 to 5, is just 5. Well, now I've got it, at least I've got it narrowed down to numbers. And now you just have to complete this calculation, which I got 55 minus 30 plus 5 for that. And then when I multiplied that by 4/25, I got 120 over 25. And then when I added it to 25, I got 101 over 5. And then when you multiply that by 2/5, you get 202 over 25, which is 8.08, which was actually what I got up here for the right side. But the point is that I was able to get a formula here. Basically, I was able to get a formula here in terms of, and then I could just plug in, the values for n. N is 5, so 5 times 5 plus 1 times 2n plus 1, and then over here for I, 5 times 6, so n times n plus 1. Well, what if we don't know n is 5? What if we just say n is n? Okay, then that's where we're headed. But anyway, if you tried the calculations with n equal 10 instead of n equal 5, then the width would be 1/5. And I'll just let you read through these calculations here. But if you let n equal 10, you basically go through the same process, but you're just using a different value of n. Well, now you'll get it to 6.92 to 7.72. So you narrowed the window a little bit. Now, we can generalize this as follows. Consider a plane region bounded above by a non-negative continuous function, which is what we had. The region is bounded below the x-axis and bounded on the left by x equal a and on the right by x equal b. Now let's consider the ith subinterval. So we're talking about the ith subinterval on the interval from a to b. So below, notice the blue rectangle. The left endpoint of the rectangle is what we would call x sub I minus 1, because it would be on the left, and the right endpoint would be x sub I. All right, so this left endpoint right here is x of I minus 1, and this is x of I. Okay, now let's try to put this together. Somewhere in the interval is a point where f of x is a minimum and a point where f of x is a maximum. So we're going to call the point that yields the minimum little m of I, and we're going to call the point that yields the maximum capital M sub I, so that the minimum over the interval is f of little m of I, and the maximum of the interval is f of capital M of I. And by the way, we know that the maximum minimum exists by the extreme value theorem. So it looks like that if I do this rectangle here, if I have this so if you look at this function from this point to this point, that would be this piece of the function from here down to here. Okay, so basically what we would be looking at would be the maximum would be here. So if we looked at the maximum, we would get that rectangle. But if we looked at the minimum point, the minimum would be here at this point. So the maximum's here, the minimum's here. So if we used maximum rectangles, we would get that circumscribed rectangle, and if we used the minimum value, we would get the inscribed rectangle. So basically, that's the maximum and the minimum. Okay, now the width of each of these sub-intervals that we have here, I've already told you that's the right endpoint minus the left endpoint divided by the number of sub-intervals you're going to have. So it would be b minus a over n. So basically the endpoints of the sub-intervals, x naught would be a, would be the left endpoint, and then you would have x1. And so at x1, you would get x1 by adding 1 delta x, so one of these delta x's. And then to get to x2, you would add 2 delta x's to a. And then to get x3, you would add 3 delta x's, and so forth. So to get to the right endpoint, which is b, or xn, you would actually add n delta x's. Okay, so and a would be a number less than a plus 1 delta x, and a plus 1 delta x would be less than or equal to a plus 2 delta x's, and so on. And then they would all be less than or equal to a plus n delta x. Okay, kind of getting the picture here. So this would be, so this down here, this down here would be a, this would be a plus delta x, this would be a plus 2 delta x. I'm going to just say this is a plus I delta x. Just pretend like this is kind of out there, several sub-intervals out there. So this point would be a plus I delta x, and then this point would be a plus I plus 1 delta x, and so on. So what we want to do is we want to find the upper and lower sums. Well, the upper sum would actually be the sum of all those rectangles based on the maximum, and the lower sums would be all those rectangles based on the minimum in the subintervals. So in our particular picture, since the graph is increasing on this picture, then the area of our inscribed rectangle, so let's go back to this rectangle. So this green rectangle here, we would use an inscribed rectangle, okay? And that would be, the height would be f of the little m, the f of the little m. That would be that would give me the height of the inscribed rectangle. So the area would be f of little m delta x. But the circumscribed rectangle, now in this particular picture, which would be this one, then we would be using f of capital M, and f of capital M represents the maximum in that interval. So the maximum gives us the height of the circumscribed rectangle. So therefore, if we got the area of one rectangle, then the area of the inscribed rectangle would be less than or equal to the area of the circumscribed rectangle. So if we sum all of the smaller rectangles, we would get what's called the lower sum, which would be the sum of I equal 1 to n f of little m delta x. And then the upper sum would be the capital S of n, which would be the sum of f of capital M delta x. And that would be the area of all of the circumscribed rectangles. Now, in this one, we sort of change directions on you because this is an increasing function. So let me show you how to find the upper and lower sums for the region f of x equal x squared from 0 to 2. Now, let's just take a look at one rectangle. Okay, so you can see for the lower sum, looks like the left endpoint would actually give us the height of that rectangle. Okay, so this would be inscribed rectangles, and this left endpoint would give us the height. Well, this left endpoint is the I minus 1 value, where the right endpoint would be the ith value. So we got the I minus 1th value. So let's see if I can kind of explain that to you. Well, since we're going from 0 to 2, delta x is going to be 2 minus 0 over n, which is 2 over n. So for the lower sum, like I said, we're going to use the left endpoint. So the value m sub I, since it's the left endpoint, is going to give me I minus 1 delta x. Well, since we're squaring, since we're going to square f of x, we're going to plug that back in the function. By the way, delta x is 2 over n, so we have I minus 1 times 2 over n. And now, to get this lower sum, what I'm going to have to do is I'm going to have to sum all of those rectangles, and each rectangle is going to have width 2 over n, and height. The height is going to be f of 2 times I minus 1 over n, where I runs from 1 to n. So by letting I run from 1 to n, we're actually going to be adding up all of the rectangles. Okay, and there's going to be n rectangles. So that's what we're going to have. Now, when you plug this into the function x squared, you're actually going to square this, and so you'll end up getting this expression, and then you have 2 over n, and I just pulled it on the outside. Okay, so when we sum all of this, let's see, we've got 2 over n. This 4 factor, I put it over here, and so that's where I get the 8. And then I brought the n squared out here, out of the denominator. And so I have 4 over n squared, so I'm going to multiply that by 2 over n, and so that's where I get the 8 over n cubed. And then I'm just going to use my formula for sum of I squared, sum of I, and then of course sum of 1. Well, if you use the formulas for each of these from 1 to n, then for I squared, you're going to get n times n plus 1 times 2n plus 1 over 6. For I, you're going to get n times n plus 1 over 2, and that's going to be multiplied by 2. And sum of 1 is just going to be n. And now you can do a little bit of cleaning up here. 2 over 2 cancels. Let's see. Now, actually, let me see what I did here. Okay, I factored this n out. Okay, I factored this n out. So I factored an n out and put it over here. So you have 8n over n cubed. Well, that's going to give me 8n squared. Okay, now I need to get a common denominator. So I'm just going to tell you I got a common denominator, and then I combined all the terms. Okay, and I'll let you do that algebra. And so I got 2n squared minus 3n plus 1 all over 6 over 8 times 8n squared. And then when I multiplied 8n squared through there, I got 16n squared minus 24n plus 8 over 6n squared. If you break this up into 3 separate terms and reduce each fraction, you get 8/3 minus 4 over n plus 4 over 3n squared. And that represents the sum of the inscribed rectangles. In the next video, I'll show you the sum of the circumscribed rectangles. And you'll see that they kind of look the same, but they're not quite the same. So stay tuned for the next video.